Hey everyone, in this video, there's no new content. We are going to be going through some of the content from Unit 5. I have it more or less structured in a way that it will be the order that we learned it in. And I've got some examples and just some key information. And so hopefully this gives you some practice and review to begin studying for your upcoming test. You guys have access to this PowerPoint, so you're more than welcome to print it out or use it as a resource as well. So with that being said, let's get started after we admire this really awesome font that I just got. Okay. So we started off, and when we started this unit, we talked about factoring. And factoring wasn't new, but there was a new type of factoring. So factoring is super important, obviously, in this unit, but also in future units where it will kind of be embedded in the skills, right? And we saw that as we moved forward in this unit as well, where you need to have the fluency in factoring in order to successfully be able to do other things, right? So we knew how to factor trinomials, right? That wasn't new to us in this unit. Difference of squares, factoring by grouping, and then what was new was sum and difference of cubes. And what I want to really emphasize right now is that you should be completely factoring, like as much as you possibly can. Like you want to break it down into its prime factorization where you can't break it down anymore. So before you kind of like circle your answer and move on, like take a look at it and be like, is there anything else I can do with that? Am I sure I'm done? So let's take a look at two examples right here. So this first one kind of looks like sum or difference of cubes, but 3 isn't a perfect cube or isn't a cube, and 192 isn't a cube. But so let's see. I'm gonna start with something. And remember, I'm factoring these expressions, so I'm just gonna be re-expressing them. Anything I do isn't gonna like disappear. I can't divide through by a number and it goes away. This isn't equal to anything. So remember the difference between factoring and solving and an equation and an expression. So I'm going to start off here and I'm going to actually factor out -3. And when I do that, I'm going to be left with x cubed minus, I believe, 64y cubed. So what I just did when I factored out that greatest common factor, if I take a look at what's left in my parentheses, this is difference of cubes, right? And hopefully you remember, and this was modeled for what does it look like geometrically, right? Like when we looked at volume in that one of the lessons. If you have a cubed minus b cubed, difference of two cubes, it factors into a minus b times a squared plus ab plus b squared. And so that's what we're doing here. And what many of you guys have done is you stop at this point and you recognize that a is x and b is 4y. Right, and so just to make sure that you know that this is actually x cubed minus 4y cubed. So you're not dropping the 64 or the 4 in there, right? And sometimes this can help you to organize your work. So now I can go ahead and actually factor it. I don't want to lose the -3, bring it down. And I've got x minus 4y, a squared, so x squared, ab plus 4xy plus b squared, so plus 16y squared. This is not factorable anymore. You can try to factor it, but it's not, right? Because it's in that form AB instead of 2AB. So this was using, we had to factor out a GCF and then recall and use difference of cubes. In the second one, hopefully your first thought is there's 4 terms. I'm going to go ahead and factor by grouping. Right? And when I do that, my greatest common factor of the first two is 9x squared, and I'd be left with x minus 5. And then of the second two, it's minus 25, negative 25, and I would be left with x minus 5. So now that I have this, if I think about you've got a number minus another number, well, these two numbers have a common factor, and that common factor is x minus 5. Oh no, not the eraser, right? The x minus 5 here. They both have that x minus 5, so I'm going to go ahead and actually factor that out. So I'll factor out x minus 5. When I do that, I'm going to be left with 9x squared and negative minus 25. Right? And so I'm not going to jump to conclusions and say I'm done. I'm going to take a look at this and hopefully recognize that there's something more that I can do. Right? If I take a look at this second factor, this factors more. It's not completely factored. This right here is difference of squares. Difference of two perfect squares. 9x squared is a perfect square, as is 25. So I've got x minus 5, 3x minus 5, 3x plus 5. Right? And so when you have those conjugates, it ends up making that middle term cancel. And I would end up with 9x squared minus 25. Okay, and so this is completely factored. So where we went from this was we started talking and we focused on cubic functions, and we looked at, I guess we looked at some polynomials in general and some of the characteristics, but then we really honed in on cubic functions, and there was some specific things that we wanted to identify when we were sketching a graph of it, right? So it's almost like you're piecemealing a graph together, like you're coming up with this composite sketch, even if you don't know all of the characteristics. And so one of those things was about the behavior of the extrema. Right? And are there extrema? Right? It's almost, is there two extrema? Is there a maximum and a minimum? Or is there no extrema? And this is, remember, specific to a cubic function, this formula right here. So b squared minus 3ac is kind of like the discriminant, right? And so if b squared minus 3ac is greater than 0, that means that we're going to have both a maximum and a minimum. That's also going to indicate that we're going to have either two increasing intervals and one decreasing, or two decreasing and one increasing, right? Because it's going to change directions. Whereas if b squared minus 3ac is less than or equal to 0, there's going to be no extrema. And so your cubic function is either going to increase the whole time or decrease the whole time. So in one of the earlier lessons, I did kind of spiral into how do you use this combined with the point of inflection to actually figure out what the extrema are, or what the x values of your extrema are, and resultantly, what are the y values. That is not something you're responsible for. So without a calculator in front of you, you don't need to come up with the actual extrema. You just need to know, are there extremas, so that you can sketch your graph accordingly. Okay? So regardless of there being extrema, there's always a point of inflection. A cubic function will always change from concave up to concave down, or concave down to concave up. There will always be one point of inflection for a cubic function. It doesn't matter if there's extrema, right? So in order to find the point of inflection, we have this formula, negative b over 3a. If we want to figure out the y value, we would go ahead and plug it back in. Right, so that would give us the x value. Concavity, we don't need the y value. So be smart about that. If we are not asked for the actual point of inflection, there's no need to spend our time plugging it back in, right? An interval where something happens is going to be x, right? Like x is kind of like time, like it's over a span of time. When is something happening? Not how high up does it go, or what's the height when it happens. So concavity, it's the point of inflection is where it changes between concave up and concave down. Remember that concave down looks like this. Oh, I said it and then I drew it in the wrong place. Concave down, concave up. Okay, and so regardless if my cubic function looks like this, I'm going to have a point of inflection and it's going to be concave down, concave up. If mine looks like this and I don't have extrema, I'm still going to have a point of inflection where this is concave up and this is concave down. Okay, and again, you have points of inflection when it's a higher order polynomial, but you're not responsible for that, right? Calculus will take care of all of that. And then finally, we also learned about the end behavior, and we learned the importance, hopefully, of notation. Right, so not just saying on the right it's increasing or it's going up, and on the left it's decreasing. Okay, so the format is, this is right, We control it. We control x. That's the independent variable. So as x goes to infinity, f of x, name the function. Is it f of x? Is it y? Is it k of x? Is it h of x? Like, pay attention to the name of the function. Right? So on the right, as x goes to infinity, what's happening to f of x? Well, if we're dealing with a cubic function, that's a third degree. Maybe I should write that somewhere. So we need to pay attention to the leading coefficient. So if my third degree polynomial has a positive leading coefficient, well, it's going to look, I don't know what's happening in the middle, but my ends are going to behave like a line, an increasing line. So as x goes to infinity, f of x would go to infinity, or whatever the name of the function is. Whereas as x goes to negative infinity, that's the left, f of x is going to go to negative infinity. So we control this piece of it. If it says left, you need to know that it says x goes to negative infinity. It's just like a number line. If it says right, you need to know that means as x goes to infinity. Okay, what this is leading to is limits eventually. So let's take a look at an example. And so I gave you one actually in factored form instead of standard form, which I think we're a little bit more familiar with for a cubic function. So I'm going to graph and label and identify these key characteristics. I can actually do domain and range right away. They're both going to be all real numbers. Well, why? Well, the domains of any polynomial is going to be all real numbers. It's continuous. The range is all real numbers because it's cubic, right? If it was an even degree, I would probably have a minimum or a maximum somewhere. I would have a minimum or a maximum somewhere, just like a parabola. But this is a third degree, so my range is going to be all real numbers. I am going to go ahead and actually jump down here and do the right end behavior. Remember, as x goes to infinity, it says right. We control this. What's the name of the function? H of x goes to, well, my leading coefficient is positive, so it's going to go to infinity. Third degree, leading coefficient positive. The next thing that I want to do is the y-intercept and the concavity. Okay, so I am going to actually expand this. So I'm going to multiply the first two first. That's going to give me x squared, 2x minus 2x minus 8, and then x minus 5. And then I'll multiply that out. So it's going to give me 2x to the third minus 2x squared minus 8x minus 5x squared minus 10x, nope, plus 10x, right? Yeah, plus 40. And so h of x is 2x to the third, negative 2 minus 5, it gives me negative 7, so negative 14x squared. And then negative 8 plus 10 is 2, so plus 4x, and then plus 80. Right? And so this would be standard form of h of x. Notice I didn't forget h of x equals. So my y-intercept is going to be 80. Or I can write 0, 80. I'm not writing y equals 80. For concavity, I'm going to go ahead and do negative b over 3a. So negative b, 14, over 3 times a, 6. So 7/3. So I know that this is going to increase, right? And so I don't know exactly about the extrema yet, but I know that it's gonna something like this. Maybe there's extrema there, maybe there's not. So if it's concave up, it's gonna be on the second half. So it will be from 7/3 to infinity. I'm gonna go ahead now and start to actually graph this. And so I've got points at 1, 2, 3, 4, 4, 0, negative 2, 0, and 5, 0. I'm scaling it. And then I also know that I have a point at 80, right? So 10, 20, 30, 40, 50, 60, 70, 80. So that will be 0, 80. I know my end behavior is going to behave like an increasing line. So it's going to start down here and end up here. I can probably tell the way I need to sketch this, because these all have a multiplicity of 1 and odd multiplicity, that it's going to have 2 extrema. But let's show that, right? Let's show that with b squared minus 3ac. Let's show it algebraically. So b squared, I believe 14 squared is 196, minus 3 times 2 times 4. So that's minus 24. So that's 176, 172, I believe, which is greater than 0. Therefore, there's going to be 2 extrema. Okay, so more or less, I don't know where exactly it peaks, but I know it's going to come back down, go through, turn around, and then increase, right? So it might not be perfect, but I'm putting together an image of it. My last thing I want to know, which is important for graphing, I do want the y-coordinate of the point of inflection because I was asked to graph it, and so that's an important piece to graph. So I'm going to actually just plug it back into this one, the factored form. I think it might be nicer than actually trying to, what's it called, square and cube. Ooh, not 7/4, 7/3. Sorry about that. So 7/3 minus, what is that, 12/3. 7/3 plus 2, so plus 6/3. So I'm just doing a common denominator, and then 7/3 minus 5, so 15/3. Then I've got 2 times, I think that's negative 5/3, 13/3, and then 7 minus 15 is negative 8/3. And so let's see, what's that going to give me? I've got 5 times 8 is 40, times 13 is 520, times 2 is 1040. Yeah. Over 3 times 3 times 3, which is 27. Right? And so that's going to give me, let me think. Does that make sense? Yeah. Right? So it's going to be like 46 point something, 45 point something. So if I just plot that, 7/3 would have been a little bit more than 2. And so like right up here approximately. 7/3, 1040 over 27. Okay. So here, and I did a lot in one problem, some characteristics and a sketch of my 3rd degree, my cubic function. We then built on that, and we started looking at higher order polynomials and sketching those. And so we weren't focused on the extrema or the concavity here, right? This was really drawing on the axial intercepts. So using the end behavior, which came from the leading coefficient and the degree, and the axial intercepts, and the multiplicity of your zeros, your real zeros. So end behavior came from the leading coefficient and the degree, right? If it was, I can come up with them all. If it was a positive leading coefficient and an even degree, it was going to behave like a parabola opening up. If it was a positive leading coefficient and an odd degree, it was going to behave like a line that was increasing. If it was a negative leading coefficient and even, it was going to behave like a parabola that opens down. If it was a negative leading coefficient and odd, it was going to behave like a decreasing line. The axial intercepts, so both x and y intercepts, remember when you're writing them down, it's not x equals. And using the multiplicity of the zeros to determine, is it touching and turning around or is it passing through? Right, so what's exactly happening at that zero? So let's take a look at this first example. So graph and label and identify these key characteristics that I've written down, a p of x. So this is in factored form, which is good. We like that. And so I'm going to go ahead and identify the degree. So, well, my leading coefficient is, it's actually not -3 because I also have this 2. So when I were to multiply this out, my leading coefficient would actually be -6. But regardless, it's negative. So now I want to focus on the degree. There's no factor that goes with this. It's just -3. It's not -3x. This 0 happens twice, so 2, 1, and 1. So that means that my degree is 4. So it's a negative even degree. It's going to behave like a line. In fact, I can even draw these arrows on here. Right? Therefore, my left end behavior is x goes to negative infinity. What's the name of my function? P of x is going to go to negative infinity. I know that right away. The zeros with their multiplicity, 2 has a multiplicity of 2. -4 has a multiplicity of 1. And then 1/2 has a multiplicity of 1. So if it has an odd multiplicity, remember it's going to pass through just like a line. If it has an even multiplicity, it's going to bounce back. It's going to kiss it and turn around, just like a parabola whose vertex is at the is one of the zeros. So I'll plot those while I'm here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I've got a point right here at 1/2 0. Got a point at -4 0. And then a point at 2 0. And then I want the y-intercept. So that's where I'm going to go ahead and plug in 0. So -3 times, if I plug in 0, that'll be a 4. That'll be a 4. And that'll be a -1. So 4 times 4 is 16. -16 and -3 is 48. Yeah. 10, 20, 30, 40, 50. So like right here. 0, 48. Okay, so let's see. When I get to -4, it's going to go through because the multiplicity is odd. And it's going to turn around at some point as best I can. Oh, goodness, that doesn't look like a function. I have to fix that. So sorry. Can I make that slightly better? Okay, at 1/2, it's going to go through it. And then here at 2, it's going to bounce back. Okay, not my prettiest graph. I was trying to make it look like a function here. I didn't do a great job, but it's getting better. Okay. So degree and leading coefficient tells you how does it behave, the zeros and their multiplicity. Pay attention to the name of the function. Make sure that your notations are correct, that you're not saying something equals when it's on an equation, when it's on a line. Okay. So from there, we went then in the direction of polynomial division, which still, the graphing and the characteristics are still important to us. But polynomial division, as well as synthetic division, kind of opens up the ability to be able to factor something that's not in standard form, that's a higher order polynomial, right? Like if we give you a 0, or you found a 0 from your calculator, if you wanted to determine if something was a 0, right? That's what polynomial division and synthetic division allows us to do. So the important words that we talked about were quotient, remainder, factoring, and complex solutions. And I wanted to put this on here because complex is all numbers, right? So this is real and imaginary, the ones that we see and the ones that aren't on our XY coordinate grid. That's what complex is. So even if all of the solutions are real, if all of the x-intercepts are real, all of it, it's a third degree polynomial and there's 3 x-intercepts, those are complex zeros, okay? So the big thing here is like, just remember to read the question and see like, what is it asking you to do? Instead of just kind of spitting out all of these things, being like, these are all the things I know how to do. Like, what is the question actually asking me to come up with? And how do I demonstrate that I know that? So is it asking me for the quotient? Is it asking me to write it in a specific form? Is it asking me to identify the remainder? Does it want the polynomial in factored form? Name it, right? If it wants the polynomial in factored form, don't just say x plus 2 squared times x minus 3. Maybe it's h of x equals. Like it is an equation, so pay attention to that. Or does it want the solution? So does it want you to go one step further after factoring? So here, we're going to divide this polynomial by 2x minus 1, and we're going to write the result like this. Okay, Delta Math has great practice with this. You guys did some homework with it, but can go back and do even more. So I'm going to rewrite it. Oh, I think I was missing a term, and I want to actually write a 0 in for it. Personal preference. And this is getting at long division, not synthetic. So that's why I'm using long division. 2x minus 1. 2x goes into this. 4x to the 4th. It means this is 8x to the 5th. minus 4x to the 4th. I like to write that 0 in so I don't forget that this is actually positive now. And then I'll bring that down. That goes into that 2x to the 3rd times. That's 4x to the 4th minus 2x to the 3rd, subtract. 6 minus negative 2 gives me 8. And then I'll bring down that 2. Goes into that 4x squared times, which gives me 8x to the 3rd minus 4x squared, subtract. That gives me 6x squared minus 7x. I might write that right here. Okay, 2x goes into 6x squared 3x times, and that's going to give me 6x squared minus 3x, subtract. Cancels negative 7 minus negative 3, gives me negative 4x, and then I'll bring that 11 down. 2 goes into negative 4, negative 2 times, which gives me negative 4x plus 2. And that's going to give me a 9, which would be my remainder. So it wants me to write it in this form, so I'm going to go ahead and write it. 4x to the 4th plus 2x cubed plus 4x squared plus 3x minus 2 plus the remainder over the divisor, right? This question didn't ask me, is it a factor? I'm not going to write, it's not a factor, right? It asked me a specific question, and that is what I did, okay? That's how you demonstrate that you really understand what the question is asking. I don't need to just give all of the things I know about it. Let's do another one. So I'm given that x squared minus 4x plus 4 is a factor of this polynomial. And I want to write f of x in factored form and then graph and label it to kind of tie it together. So I'm going to start with division, right? This is a quadratic factor. I should get a remainder of 0, but I'm not going to do synthetic division because right now it didn't give me the zeros, and we're practicing long division right now. X squared minus 4x plus 4. It goes in 2x times. So if I divide a 3rd degree by a 2nd degree, I should just get a linear factor here. So 2x to the 3rd. What is that? 2x to the 3rd minus 8x squared plus 8x. Subtract, goes away. That becomes 3x squared. Negative 4 minus 8 gives me negative 12x plus 12. That goes into that 3 plus 3, so that's going to be 3x squared minus 12x plus 12, which, amazing, they all cancel and give me 0. Okay, so I have right now, I'm going to just write it up here, f of x equals x squared minus 4x plus 4 times 2x plus 3. This quadratic factor that I was given actually factors more, so it's f of x equals x minus 2 squared times 2x plus 3, right? And so this answers the first question that I was asked. Or notice that I have f of x written. I don't have an expression, I wrote the equation f of x. Then it says to graph and label it. So this is a 3rd degree. So I have a point at 2, a point at, what is that, negative 3 halves, 2, 0, negative 3 halves, 0, 12, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 0, 12. Let's do the point of inflection, negative b over 2a. So 2 times a, so it's 5/4. And then I'll actually just plug that back into the factored form. So that's going to give me 5/4 minus 2 squared. And then 2 times 5/4, so 10/4. No, that's fine. Plus 12/4. So let's see. Negative 3/4, which is going to be 9/16 times 10, 22/4, or 11 halves. 99 over 32. Okay, and so I'll graph that. I'll plot that as best I can. I'm going to be obviously approximating because that's like almost 3, a little bit more. Okay, so my end behavior, it's going to behave like a line that's increasing. So I'll start down here. When I get to negative 3/2, it only happens once, so it's going to go through. And then, I don't know, it's going to turn around somewhere and come back. And when it gets to 2, it's an even multiplicity, so it's going to touch it and turn around. What was it? 5/4, so a little bit more than 1. Yeah, that's not my greatest point. That's okay. Right? And that's where it changes concavity. Right? So kind of tying it all in together. Think about what you can do. Synthetic division, right? And so it's kind of similar ideas, the quotient, the remainder, write it in factored form, find the complex solutions. So in order to use synthetic division, you need to have linear factors, right? You need to be working with the zeros instead, oh boy, instead of the factors here. So if I'm giving k of x right here, I want to use synthetic division to determine which of the following, if any, are factors. So this is really, eventually you'll learn about the rational root theorem. If it's something you want to look up, go for it. That will generate a list of rational zeros of a polynomial, if there are any rational zeros. You'll also learn a way to figure out how many rational zeros there are, or how many there can be. So I lost my train of thought. So synthetic division is a really quick way to kind of just check it. So I'm going to go ahead and let's see, 2, -3, 1, I'm missing a term, 0, -6. I'll start with A. So -6. So I can see 2, -12, -15. 15 times 6 is 15, 30. 30 times 3, 90. 91, oh goodness, 91 times 6 is going to be 156? No, it's not. 146. No, 546, sorry. And you can kind of see what's happening here, right? So this is 546, -546, so I get -546. I mean, it's not going to give me 6, right? So I know that this is not one of them. Okay, so let's try the next one, 2/3. 2, -3, 1, 0, -6. And what is that? 4/3. What's -3 plus 4/3? Gives me -5/3, right? That's going to give me -10 over 9, which is going to give me 9. 9 minus 10 is negative, so -1/9, right? -1/9 times 2/3 is going to give me -2 over 27, which is going to give me -2 over 27. Oh, sorry, I wrote that wrong. And then when I multiply that by 2/3, it's going to give me 16 over 27, which is not going to give me 0. Right? Like I can see that it's not working. Okay, so that's off my list. Let's try -1. 2, -3, 1, 0, -6. 2, -2. -3 times plus -2 is -5. 5, 6, -6, -6, 6, 0. Woohoo! This right here is one of them, right? So, I've now got this. So now I've got a 3rd degree polynomial. And I can see, like, what do I do with that now? Let's see if 3 is 1. 2, -3. 1, 0, -6. 2, 6, 3, 9, 10, 30, 30, 90. Nope, certainly not. 84. Nope. right? So I was able to identify using synthetic division which one of these is actually a factor. Pretty cool, right? And then finally, what we kind of finished up with was the factor and remainder theorem. So it determines if a given factor is indeed a factor and determines what the remainder would be if it was divided. Right, so here I can, use the remainder theorem to determine what the remainder is of p of x if it's divided by x minus 3. And so use the remainder theorem to determine, so I'm just going to go ahead here and basically I'm finding what is p of 3. Right? And so I can plug in and say 3 to the 4th power minus 2 times 3 to the 3rd minus 3 times 3 squared plus 4. So what is that? 81 minus 54, 9 minus 27 plus 4. Hopefully all my math is right there. I'm sure someone will tell me if it's not. Which gives me 7. Right? 3 to the 4th, let me think about that again, is 81. 3 to the 3rd is 27 times 2 is 54. And then 9 times 3 minus 27, so 81 minus 54. Good. Minus 27. And then plus 4. Oh, wait, no, it's 4. Right? Because these together, 54 plus 27 is 81. So these would cancel and give you 0, and then I'd get 4. Right? So my remainder would be 4. So actually, I do know one of the points on p of x. I know the point 3, 4. But this isn't a factor, right? So my remainder, when p of x is divided by x minus 3, would be 4. Use the factor theorem to determine if x plus 4 is a factor. So I'm going to find p of negative 4 here. So negative 4 to the 4th. This is a test of my mental math here again. Minus 3 times negative 4. My quick mental math, I guess is a better way to say it. So let's see. 4 to the 4th is 6. 256, 64, negative 64 times 2, right, is going to be 120, plus 128. 16 times 3 is 48, right? So minus 48, and then plus 4, right? 250, positive 256, that would be negative 64 times negative 2 gives me positive 128. So then 256 plus 128 is going to give me 356, 360, 36, 376, 384 minus 48 plus 4. So 384 minus 48 is going to be 336 plus 4 is going to give me 340. Right? So use the factor theorem to determine if x plus 4 is a factor. X plus 4 is not a factor, right? Because p of negative 4 did not equal to 0. Okay? So just knowing like what each of these mean and what they're asking you, and just read the question carefully and pay attention to those little pieces. So hopefully this gave you a nice overview of the unit and was able to kind of help you to narrow in on what might you need more practice on and what resources on the current page do you need to go back and reference. So other than that, make sure that you're working on the Go formative and using any of the feedback that you may be given to help review for your upcoming test. And we will see you all soon.